Hello, everyone, and welcome to today's webinar, Improving Security Forensics in Kubernetes Environments. I am pleased to introduce today's speaker, Christopher Leonstopi. He is the original architect behind Tigera's Project Calico. He is a speaker at over 60 meetups a year, so he's educating lots of people on networking, network security for modern applications, microservices, and containers, etc. He also consults Tigera's enterprise clients on security and compliance for their applications. So before I hand the mic over to Christopher, I have a few housekeeping items I'd like to cover about this presentation and the webinar platform interface. First, today's webinar will be available on demand after the live session is over and will be accessible through the same link that you are using now to watch this. We've also added some attachments and links which are available through the Attachments tab. There you will find other related content if we had content for that. If you would like a copy of today's slides, these will be sent out to you by email after the session is complete. And we'd love to hear from you. So if you have questions for our speaker, please feel free to send them through the Ask a Question, the Questions tab. Yeah, so the Questions tab, and we will get to those questions. We might get to them as they come, but we most likely will get to them at the end of the session in Q&A. And so, without further ado, I'd like to kick.
Actually, before we do that, Michael, before we start this, another thing, we like hearing from you. We'd also love to hear from you what you'd like to hear in this series of presentations, right? If there are topics that you folks would find interesting, we'd love to hear that as well. So please reach out to us and let us know if there's specific topics you want us to cover.
Okay. Well, Christopher, it's all you.
It's all me. Okay. Well, welcome everyone. And today we're going to talk a little bit about forensics and how forensics change as we go into a containerized, specifically a Kubernetes environment, but a lot of what I'm talking about is going to apply equally to any kind of containerized environment. And we're going to talk a little bit about how, not only how you do forensics might change, some of the things you need to consider, some of the things you need to adapt for example, to make forensics data and your SIEM tools more useful, et cetera, how you deal with doing actual forensics on suspect workloads, et cetera. This is a very deep topic, so we're not going to be able to cover everything in the allotted time. So we're going to sort of give you some things you need to be thinking about and potential areas that you might want to think about your designs and maybe design differently going forward, especially as it relates to forensics in containerized environments. So let's go ahead and talk about the first case, which is how we used to do forensics on VM or even bare metal workloads. In this case, we have a VM or a bare metal host. And it's pretty much a black box. From a forensic standpoint, in the legacy days, you could take a look at what was coming in or out of that black box, coming in or out of that VM, coming in or out of that bare metal host, and Sally, the security engineer, could observe that and make forensics decisions about, is that black box doing the right thing or doing something that we didn't intend for it to do. So, that's a pretty limited amount of visibility. Those were big monolithic apps. There's lots of things going on within that black box, but we didn't have much visibility other than it goes in and goes out. And that was mainly north-south traffic too, by the way. It wasn't there wasn't a lot of east-west traffic, so mainly this is, the request comes in and the response goes out, or the request coming in turns into a request going to the next thing down in the stack, say a database server. So fairly limited visibility. So we came up as an industry with APM, and APM allowed us to instrument these black boxes and look at what's going on inside the black box. And then that might be by catching system calls. That might be instrumenting libraries and API level calls within the application. So that gave us visibility, at least at the module level or the library level, within this black box. It's now sort of a semi-transparent, a smokily transparent box. However, this had quite a bit of implications, right? If you wanted to deploy this kind of visibility, you had to compile it in or build it into your application itself. It means the developers had to all have this as part of their build process or deployment process to push this capability actually into the code, to actually make it visible. So you could get greater visibility, but you were doing so at an additional cost and complexity to the way you built your application. And if for anyone who's done APM before, gee, I want to go deploy the latest version of an operating system image or module, and then you discover that your APM tool doesn't support that yet, right? So you have another dependency in your build cycle, waiting for APM vendors to catch up with current state of the art. So, but that's the tools we've had, and people have successfully used those, even with the complexity. But what happens is we've gone through now almost like a big bang model of taking and exploding this big monolithic app into lots of microservices, right? This is the whole model behind Kubernetes and the other orchestrated environments. So now what had been one big monolithic app with a bunch of library calls, the libraries that got compiled into it, and library calls now become individual entities in the infrastructure. So instead of one VM, we now have lots of microservices and potentially multiple instances of each microservice. So that is well, that brings some complexity, and we've talked about Kubernetes and how Kubernetes orchestrates things before, and how Kubernetes corrals that complexity. It actually opens up an interesting avenue for forensics, and that is that now what had been API calls within a given executable, or library calls within an executable, now become network calls, right? All of those, what had been libraries, are now separate microservices, or can be, and now the linkage between those different components is an API call, usually an HTTP REST-based or gRPC or equivalent call across the network. So we've now exposed on the network the actual traffic between the components of our application. So you can have that built. You can manage all of those API connections yourself and build in the mechanics to do backoffs and retries and failure detection and rerouting. All of that, in fact, early on, everyone wrote all that code into each of these modules themselves, these microservices. That brings with it its own set of issues. Every developer having to basically write an API call framework and all of the tooling that needs to go around that. So, IBM and Google rolled out a project called Istio, which is an instance of a service mesh. And there are other service meshes out there, but just taking, for example, Istio here. Now, Tigera and Red Hat and other folks are actively contributing to this. This is an industry, a fairly fast-moving industry approach to service meshing. But one of the things that you get off of these service meshes isn't just retries and backoffs and rerouting due to failures, etc. You get a lot of visibility. One of the things these service meshes do is kick out a lot of data about each and every one of these API calls between the individual components of your application. And it's doing this in a way that the developers don't necessarily have to know much about the service mesh or implement the service mesh. basically the service mesh component inserts itself into each pod or container, pod in Kubernetes case, and instruments this set of connectivity, this connectivity graph, all these arrows. So we're collecting now a lot of data about who's calling who and what the payload of that was and all the characteristics of that call. So now what we used to use this very intrusive APM infrastructure tells a lot what's going on with a service mesh across a standard network. You now have visibility, very fine-grained visibility into all of the intermodule traffic or intercomponent traffic in your application. So, and when you start thinking about forensics, the best part of forensics is to collect. Pardon me. Pardon me. Too much time on planes the last week. Instead of trying to collect your forensics data post fact after you've had an incident, if you can collect more of that data up front before you have an incident, it allows you to better detect when there is an incident, indicators of compromise. Also allows you to establish a baseline and allows you to see when changes happen. So if you detect a compromise later, if you have all of this API called data basically available, you can see when behavior started changing, maybe giving you a better indicator of what was compromised and when. So, let's do forensics in advance of an event rather than after an event and collect this data and use it and analyze it. And that becomes much easier in a Kubernetes environment using a service mesh. So, no questions so far, it looks like, so we'll continue on. The next is waiting for the build. Okay, so now let's say we have Eve, evil genius Eve, and she is going to try and attack your infrastructure. So first let's have her attack that heritage VM sort of smoky box. So she attacks that VM and compromises that VM. So she now has compromised it. It is now acting as a command and control infrastructure for a botnet, or is going out and harvesting data out of your customer records database, or whatever other nefarious things she's going to try and do. And we've gotten an indicator of compromise. So Sally, some alarm is tripped, and Sally realizes that that smoky gray box has been compromised, or believes that it might be compromised. So what Sally has done classically in this environment is, it's a bare metal server. The server gets shut down and isolated, and then moved into a forensics clean room, so to speak, where it can be analyzed. Similarly, if it's a VM, you would pause or freeze that VM, and again, move it logically into a clean room where you can analyze and evaluate what happened. There's two ways of responding to an attack, right? To a compromise. One is just get rid of the compromised things. You're not interested in what happened, etc. You just want it off your network. So you can, basically shut down or kill that instance and restart, and hopefully you restart with a clean instance. So that's one approach. That's just the I want it gone approach. The other is, let's try and figure out what Eve was trying to do. And that's when we start getting into actual forensics of an attack. Now, as has been mentioned, I think before in this series, I was a park ranger in the Park Service at one time, and as part of our law enforcement training, I remember very well our officer survival instructor said, when you find a weapon on someone, don't stop looking, because people who carry one weapon usually carry more than one weapon. So let's say if I take that to heart, if I find Eve has compromised the machine, if I assume that's the, do I stop there and just assume that was the extent of the compromise, kill off the machine and reinstantiate, and I'm back in business? Or do I assume that Eve potentially, what I've detected may not be her first or only thrust of attack in my infrastructure? So maybe what I want to do is, instead of just killing it off, I want to examine it and try and figure out what else she was really trying to do, what else she might have already done, so I can actually try and more completely contain the compromise. So what was she going after? Why was what was the data she was going after, or what was she attempting to do? This is a command. Looks like it's going to be a command and control server for a botnet in my infrastructure. Maybe I need to figure out what the control channel is, so I can go find the nodes that might have already been infected and are acting as a botnet already. So there's advantages if you have the skill set to actually go and do some forensics on these components when you find them. So Sally's done that. Sally's figured out what Eve was trying to do and countered that, and life is good. But now we've gone over to a Kubernetes environment. So Sally's company is now deploying microservices in a Kubernetes environment, and Eve, keeping up with the times, attacks one of the Kubernetes pods for a given service. So we can just freeze this pod and shift it over to a clean room, forensics clean room, and start looking at it, right? Fortunately, not quite. So containers aren't really separate instances of operating systems. Containers are a memory space or a namespace within the underlying host's operating system. So it's really not a good way of freezing a container and moving it. I mean, technically it might be possible, but that's not something that the orchestrators today really do. So I can't really pick this up and move this somewhere else and then reinstantiate it, or rehydrate it and examine what it's doing. So you might think the only thing you can really do is kill that pod that's been infected and reinstantiate a new, hopefully clean one. But as we said, there's some value to actually trying to figure out what's happening. So instead of picking up and moving it, why don't we just isolate that pod? So by using a combination of what we can do with the service mesh and what we can do with network policy controls in Kubernetes, like with Tigera's solution, you can actually put a label or a piece of metadata on that pod that says that pod should be quarantined. That pod is suspect. And at that point, the service mesh, the underlying network infrastructure, Kubernetes network infrastructure, can actually isolate that pod or set of pods that has been potentially compromised and prevent them from actually communicating with anything else in the infrastructure. You take this a little bit farther, and you could say, instead of having it being diked off from everything, which might be a signal to the attacking code to destroy itself, to self-destruct, maybe what you do instead is you cut off its connections to the production environment and replace it with connections to a honeypot environment or an evaluation environment, where the attacking code may not actually notice that it's been removed from production and it continues to function, and then you can evaluate what it's doing. Again, maybe using service mesh, right? If you move it over and you point it at a honeypot infrastructure, and you're still using service mesh, then it's just, the service mesh is now pointing to this honeypot infrastructure. You can now see all the API calls it's doing, what it's listening for, etc. So in a containerized environment, you may want to quarantine or change the service mesh topology such that that pod can be evaluated, the suspect pod or pods can be evaluated without killing them and without shutting them down. Again, try and figure out what Eve's actual endpoint goal was trying to do. What was Eve really trying to do, rather than just killing off the thing that she infected. So before, so to reiterate, before you would have frozen and moved into a clean room, Here, we sort of bring the clean room to the pod rather than moving the pod to the clean room by adjusting the service mesh and instituting network policies. So before I go on with the next topic that we want to talk about, let me pause here if there are any questions. So if not, we will continue. Doesn't appear if there are any questions right now, so let's move on a little bit. So now let's talk about Eve and the way containers get deployed in something like a Kubernetes environment, the way microservices get deployed in Kubernetes. So as a general rule, most people are going to deploy their applications via some kind of CI/CD pipeline, continuous integration, continuous delivery pipeline, normally anchored to some kind of source code control system like Git, in various flavors. That could be GitHub, GitLab, Bitbucket, your own implementation, but it's some form of source code control system and versioning system. So you put your definitions and your code and your container definitions into your source code control system, and a CI/CD pipeline then deploys those instances into your infrastructure. And that CI/CD pipeline is secured and does checks to make sure that what's getting deployed is what's in the repo itself, and this has some amount of security controls around it. The idea being that what gets deployed should reflect what's in the actual repo itself. So now let's say Eve attempts, next build. Now, as we were talking about, let's talk a little bit about what those pods should be doing to support forensics. We should be collecting all of our logging data coming off of those pods. We should make sure that our actual individual components are generating sensible logging information. Just like the service mesh is generating logging information about the API calls between the pods, we really want the things on the pods, the actual microservices themselves, to be generating useful logs. And those logs should be going potentially into a couple of different pieces of infrastructure. One, we should be going into some kind of EFK or ELK stack. So that's Elasticsearch, FluentD, and Kibana, or Elasticsearch, Logstash, and Kibana. You might be using Splunk or something else as well. But the idea is all of these logs should be dumping into a large searchable store that you can then use to start building, characterizing. Let me see all of the behaviors of this given type of pod. So you should be able to search through things, look for things in the logs in an easy, sensible manner. And that's where the Kibana and Elasticsearch components come in. More importantly, you should be making sure that those logs are sensible and have long-lived data. I've talked about this before in a couple of webinars. A lot of logging systems use IP addresses, for example, as an indicator, as an identity of the endpoint. In an environment like Kubernetes, things like IP addresses or nodes and something's on are very, very ephemeral and actually may be reused multiple times in a day, let alone in weeks or months. So if all of my logs are pinned to an IP address for a given pod, that's really sort of useless because that IP address over time could refer to very different things in your infrastructure. So you really need to make sure that those logs are annotated with data that comes from the orchestrator that allows you to uniquely identify what is the thing that is being logged, what generated that log, etc. And that allows you to make sure that you can actually have sensible log data as you go do a look back to see, for example, when Eve got in and what she did. So make sure your logs are sensible, make sure they're going into something that's searchable. The other thing, you might also want to make sure they go into something that's time series based, say like Prometheus. And the reason for that is you may want to be able, you definitely want to build up baseline data. You want to be able to say that this kind of log shows up 20 times a minute across my infrastructure per n number of instances of this particular service or microservice. And then be able to set triggers to say, hey, if that log is showing up more than 20 times a minute per n number of microservices, then I want an alert, because we're now exceeding what was known as baseline. So from that perspective, we probably want to be able to using a time series database as well as my searchable log store. So just some things you want to think about how you want to manage these logs. Other things are obvious but worth mentioning. Make sure that you have accurate time across all your components so that logs can be correlated, etc. All the standard practices for an at-scale logging system. So we've now been logging all this data. And let's say now Eve wants to attack one of our microservices again. She's not given up. She's going to make an attack. So if we've done the right thing, what we've done is we've made these pods, these microservices, immutable when they're deployed. And the idea being here, in a containerized environment, troubleshooting should not be going into a given microservice, a given instance of a microservice, SSHing into it or execing into it, and making changes to the running microservice for a couple of reasons. One, it opens a pathway for attack for Eve, which we'll talk about in a minute. The other means you now have a snowflake. So let's say I have built a platform that is auto-scaling, and normally I have 3 instances of a microservice. And something's gone wrong with that microservice. I didn't get the configuration quite right. In a VM world, it's very likely you would have SSH'd into each of those VMs and changed the configuration. And that's okay. In a containerized world, that's not. Because I will have changed the configuration on those 3 running instances, but not back in the GitHub repo where that gets built. So in 5 minutes later, when Kubernetes says, I need 100 more of these to deal with a flash crowd, it's going to go instantiate 100 more that won't have that fix. So I now have 3 snowflakes that work correctly and 97 that don't. Really fun to troubleshoot that one. So operationally, you should make sure everything is fixed in GitHub, in the code repo, and then you redeploy. You say, okay, I've got a problem. I go fix it in the code repo, and then it gets pushed out through the CI/CD chain, and the 3 bad instances get replaced with 3 new good ones. And 5 minutes later, when you get the crush of users, Kubernetes deploys 97 more instances that are correctly configured. So we really shouldn't need to SSH or exec into workloads, except for maybe trying to debug a problem, as in what's happening within the pod. But that's really, you shouldn't be doing that on a live system. So, however, people tend to do what they've always done. So instead of saying we won't do that, you probably actually want to put colors around that and say we're going to block SSH into our pods. We're going to use RBAC to control such that most users or all users can't exec into a pod. Kubernetes RBAC control. So if we have done that, then it becomes very, very difficult for Eve to actually infect running workloads, because those workloads have become basically immutable. Kubernetes isn't going to allow them to change, or some external actor to come in and change them. So Eve launches an attack, and her little virus is blocked by those controls, and her attack is unsuccessful. Those pods are still running as they were deployed out of GitHub. And we're assuming what's in GitHub is known, has been evaluated, is trusted. Let's say that that's not quite a true statement. And actually, your developers got spearphished, and somehow from that spearphishing, an attacker, say Eve, gets around and actually writes bad code into your spec for a given microservice. And that is in GitHub, and then as Kubernetes deploys those workloads through that secure CI/CD pipeline, that attack is now distributed within the pods. If I've been doing logging, etc., I'll notice, for example, that the new version of those pods is actually different from the previous ones. That might be an indicator of compromise. I know that those pods themselves can't really be mutated, can't be changed. So Sally, our security engineer, goes and looks in the underlying GitHub code and finds the anomalous code that got injected, maybe a new version of a Docker container. It's a different Nginx Docker container than we normally deploy, and it happens to be a compromised Nginx container. So Sally figures that out. Sally removes that. She examines the code. She removes that security issue from within the GitHub repo. That also might have been caught, by the way, in the GitHub repo via repo scanning and those kind of things. But somewhere or another, we found out about it. We removed that from the GitHub repo, and then we do a redeployment of those same services. And what happens then is we now end up with uninfected pods. We're back in business again. So the key thing here, from a forensic standpoint, we noticed a change in behavior, and we went and found the code. If we know that those pods can't be mutated, then we know it's got to be in the origination, the source code repository. Go up there, find it. It's much easier to look in the source code repository for something that's bad than to try and reverse engineer running code in a pod. So we find it in the GitHub repo, we clean it up, we push new versions, and we're back in business. Let's say, however, we have not blocked SSH or allow all our developers to exec into pods. We haven't gotten that memo yet. So in this case, Eve's attack to those pods is successful, and those pods are compromised. So what do we do in this case? So first of all, again, we have some indicator of compromise. As part of our forensics, we noticed that through Sarah SIEM tools that there's log changes, that these things are doing different things. Our service mesh is saying they're making different API calls, trying to come up with different databases versus what they usually do, etc. So I've noticed a change in the environment that looks suspicious. So I go look in the GitHub repo, and nothing has changed there. There's been no change in the Git repo between before and after the indicator of compromise floated up. So I now have to assume that someone has been able to actually change my pods. So again, now I can go through what we talked about earlier. I can isolate those infected pods and start evaluating them, but at the same time, I don't want my service to go down, right? So if I isolate all those pods, they were supposed to be doing a useful service, useful function in my application. So let's say I now isolate those so I can evaluate what was done, but I need to get back to a known good working state. So the first thing I'm going to do is I'm going to put in the rules I should have put in the first place, which is I'm going to block the ability to SSH or exec into or otherwise modify running pods in the infrastructure. So I put in those filters, and at the same time, I redeploy with the known good in GitHub set of instructions and code base. So in that case, we redeploy. We now have uninfected, un-Eve tainted pods. And I've put in the filters in Kubernetes and with network filtering, network policy to block things like SSH and have very strong RBAC controls around execs. And now I know that Eve can't reinfect those pods, which I don't think she can. And my application is still running, while at the same time I have the isolated pods that were infected that I'm now doing analysis on, so I can maybe find what else Eve might have done to my infrastructure. So that gives you a little bit of a workflow on how you forward protect, how you can identify compromise, what you do when you've identified compromise in the Kubernetes environment, and where you might want to start collecting data to develop baselines on what is normal versus abnormal behavior in your infrastructure. So let me go on and talk a little bit about some of the things that we can do to help here in Tigera. I don't want to turn this into a product definition, product pitch, but I do want to talk just a little bit about some of the things that Tigera has that can help in this regard. So, I guess before I do that, though, let's talk about best practices. So configure your logs into a central searchable space, as I talked about, EFK, Elk Stack, maybe Splunk, or something along those lines. Also use time series infrastructure like Prometheus to detect deltas and make sure that, and identify when behaviors change over time in your infrastructure. Make sure your logs are sensible. Make sure that they use Kubernetes metadata annotations where possible so you can actually know what that thing was that threw that particular log. Use service meshes to do a number of things like make it easier to develop RESTful and gRPC API-based infrastructures, but also to collect API call data. Istio is a wonderful example of a service mesh that can do that for you, help you do that. Don't kill things that are interesting, because if you do, you lose any chance of actually trying to recreate or figure out what was done. You're flying in the dark. Instead, isolate them. Using service mesh and network policies in Kubernetes, isolate them such that you can examine them, but they can't do any more harm. Ensure that, and then the last thing is immutability. Ensure that the running pods are from a known source and you know the provenance of those of that code, and you've examined it and you've done static testing on it, all the things that you should do for code that you're going to deploy, and make sure that the pods are coming from the code base that you've done all that work for on. And if they are, try and make them immutable once they're launched so that Eve can't infect them. Giving Eve the only path is to infect through your code base, which would be easier to detect. And if you must allow immutability on pods, make sure that everything is logged. Use Kubernetes RBAC controls to know exactly what changes were made to running pods, who made those changes, and when you see those, go back and ask why, or have some kind of proactive logging facility where somebody who's going to make a change to a pod has to log why they did it, so that in case something does happen, you at least have traceability as to where it came from. So those are just some basic best practices to support forensics in a Kubernetes environment. Some of the things that Tigera can help with in this space, we can provide very detailed metadata labeled flow logs from network data in the infrastructure that not only indicate the standard IP address, 12 tuple, was it allowed, denied, etc., but indicates what policies were used to allow or deny the traffic, what namespaces the endpoints, the source and destination were in, what network policies were used, what network policies were used to allow or deny, and even what metadata labels were attached, what Kubernetes labels were attached to the source and dest. And the Kubernetes name, for unique name for that source and dest. So this gives you actually a very detailed log, so you can see exactly what things were involved and what the configuration was that allowed or caused traffic to be allowed or denied. We also give you the ability to dive in and explore your connectivity and your infrastructure, and we can scope this down by allowed or denied traffic, by namespaces, by pod types or instances. So we allow you to visualize very clearly all the flows of traffic that are in either across your whole application space or a given application. So it allows you to visualize the connectivity that your application components are performing. And lastly, and we can filter these by namespace, name, status, etc., as I said. And lastly, we can give you policies that allow you to control traffic all the way from layer 3 to layer 7, such that only endpoints, labeled Bob can talk to endpoints labeled Alice on port 443, but may also only do so if they're using the right TLS certificate and they're making the right kind of HTTP or gRPC query. So this gives you the ability to control those APIs all the way up to layer 7 now, as well as layer 3, layer 4. And this is how you would implement, for example, quarantining, as well as just controlling the service graph to begin with. So those are some capabilities that we give you. There's others. There are other platforms out there as well, but I think here the idea is, you need to rethink a little bit how you do forensics in the Kubernetes environment, and take advantage of some of the capabilities that Kubernetes has that may not have been present in more heritage kind of environments. And with that, I'm done with this. I'm interested in hearing any questions, and I'm going to turn it over to Michael.
Yeah, before we get to the questions, we just have a couple of words from our sponsor. So there is actually a Kubernetes Network Security Made Easy guide that is available for download. It is free, and then you can go to that link and grab it. It's a very technical, informative document on how to implement network security in Kubernetes. So definitely have a look at that. And also coming up, our next webinar will be on Wednesday, October 10th at 10 a.m. Pacific, 1 p.m. And the subject is, what is policy and how does it enable Kubernetes security? So it's a very, very top of mind topic for anybody who is implementing running Kubernetes and is interested, of course, in making it secure. And that is available on our Bright Talk channel that you guys are all signed up for. So you can go ahead and sign up for that webcast with one click of a button. So it's very easy. And so with that, we don't have any questions yet from our audience. So if anybody has a question, please do go ahead and ask. And this shows you how much of a non-marketing hype product show that this presentation is that we don't come here with canned questions that are softballs. We want to hear from you guys. And as Christopher said, if you have any ideas for topics that would be valuable for you, that would be great if you could put those into the chat, or you can also send them to reply@tigera.io, and that goes to me and the marketing team, and we look at those emails. So I'll give it a couple of other minutes for you guys to type in a question, but if this was pretty clear and you guys don't have questions, then we may have achieved our goal. Okay. All right. Well, once again, thank you guys for attending. A copy of this webcast and the on-demand version link will be sent to you guys as soon as it's processed and done, probably sometime today. So once again, thank you for attending, and we hope to see you at our next webinar coming up soon. Thank you.